Think of a traditional computer program as a fixed mechanism. You write specific instructions, if this, do that, and the machine follows them with total rigidity. This works for simple calculators, but real-world problems like predicting house values or identifying spam involve too many variables and shifting edge cases to manually hard-code every possible scenario. Machine learning reverses this approach. Instead of providing the system with rules to solve a problem, we provide the correct answers and let the system calculate the rules itself. This requires a dataset, a large collection of historical examples that serves as the foundation for the learning process. To make sense of this data, we separate these points into features, the input variables, like a property's square footage, and labels, which represent the final output, such as the actual sale price. By identifying the relationship between features and labels, the computer stops following manual instructions and begins the process of pattern discovery. This occurs during the training phase, where the machine actively processes the dataset to refine its internal logic. In supervised learning, the model analyzes historical data, where the correct outcomes are already provided. It makes a prediction, compares it against the historical record, and adjusts its parameters until the error rate drops. Unsupervised learning is used when no labeled outcomes exist. The model is fed a mess of raw information, like thousands of individual customer purchases, and must identify hidden clusters and structures on its own. Reinforcement learning functions through a continuous feedback loop. An AI agent interacts with a dynamic environment, receiving rewards for successful actions and penalties for failures until it finds the optimal path. Regardless of the method, the objective is to build a model that captures the mathematical logic of the environment it is being asked to simulate. However, a model that performs perfectly during training can be functionally broken. If the evaluation is based solely on how well it handles familiar data, the system may fail the moment it encounters a new scenario. This failure happens when a model falls on either extreme of the bias versus variance trade-off. This chart shows bias, or underfitting. The model is too simplistic, drawing a straight line through curved data. On the other side is high variance, or overfitting. The model perfectly touches every point, memorizing noise rather than the signal. A model that has merely memorized the past is incapable of interpreting the present. It has failed to learn the underlying concept, making it useless for any practical application. To prevent this, engineers must introduce constraints that stop the model from taking the easy path of memorization. The most direct solution is increasing the volume of data. By exposing the system to more examples, it becomes harder for the model to memorize specific points, forcing it to find broader trends. Engineers also apply regularization. This adds a mathematical penalty to the training process, discouraging the system from creating the overly complex, convoluted rules that lead to overfitting. Another method is dropout, shutting down random network connections to force robust internal logic. Finally, data augmentation alters training examples, like rotating images, ensuring the model learns core features rather than specific orientations. These intentional hurdles strip away the model's ability to cheat. By surviving these constraints, the system develops a generalized understanding holding up in the real world. This leads to the final stage, inference. This is the moment the trained model is put to work on data it has never seen before. Instead of relying on a memorized answer, the model applies its learned patterns to new variables, predicting house prices or identifying spam with high accuracy. The value of the system is found in this transition, the ability to take observations from the past and use them to successfully navigate the variables of an unknown future.